Hello, and welcome to session B16, Going the Distance, Testing Network Impacts on DB2. My name is Mark Murnane, and I'm part of the European Technical Sales team for DB2 at IBM. As you have all probably experienced, the database frequently gets blamed for performance issues, either in application or batch jobs. But we all know that frequently the causes are outside of DB2. As professionals, we do our best to test and understand these factors, such as server and storage performance. The network, however, is a huge factor in ensuring that everything runs smoothly, but all too often assumptions are made about its reliability and performance. In this session, there are 4 high-level topics that I'm going to cover with you. First of all, we'll explore some of the aspects of networking that can cause issues. Next, we'll briefly look at where DB2 is impacted by poor networking. The meat of this session is in simulating network effect, where I'll introduce the Linux traffic control mechanism. Finally, we'll go through 3 practical scenarios where we can apply traffic control with DB2. So, why does this matter to a DB2 professional? Well, fundamentally, this is all about performance. As DB2 professionals, we constantly look at performance of our systems and tune them to strike an optimal balance between availability, resources, and business requirements. The network is a vital piece of infrastructure for any database system. It's the conduit not only for servicing data requests, but ensuring resilience and business continuity. An inadequate network could jeopardize the success of an organization. Unlike a lot of other components, however, it can be hard to test different network configurations. Traditionally, we work in the same organizations or have close contact with the providers and operations teams, but cross-site networking may involve many unknown or uncontactable operators. Similarly, LAN environments are generally reliable with consistent performance. But can you saturate your WAN links safely without being flamed? Much of this presentation will be about simulating conditions on different network links. Another reason why this is important to us is that due to changing business needs, there's an increasing need for 24/7 operations or reduced costs, and many of you are using or will be exploring cross-site operations or moving applications to cloud. So while the server and storage requirements for our workload may be known, we need to understand if or how a WAN will change things. After all, we're all used to a database getting blamed for poor performance, so it's always useful to have some data to bat back any issues. Of equal importance is user perception. If users are unhappy, we're unhappy, and the network helps shape that perception of our service. It's important we understand what the experience of the user is or could be. So as we go about testing our architectures, both new and existing, there are a number of questions we can ask. From a capacity perspective, does the network give us enough capacity for what we need? From a resilience perspective, will the database perform with an unstable network connection? If we look at resilience and performance, we can ask the question, how far is too far? And finally, can we successfully move our database or application to the cloud and maintain our service levels? So let's start then with the network effects. So what factors affect network performance? When asked to describe a network connection, bandwidth is probably the thing people think of first. Most probably you'll cite the theoretical throughput of the bandwidth, but in reality, how wide is that pipe? That depends not just on the length of the maximum throughput. Start again on that one. What factors affect network performance? Bandwidth is probably the network metric people think of first when they're asked to describe a network link. And most likely you'll cite the theoretical bandwidth at that link, which is how much data we can transmit in a given time slot. But in reality, how wide is that pipe? That depends not just on the theoretical bandwidth, but also on the protocol we're using. Some are chatty, some are very light, but the protocol bandwidth is what we work with mostly. Throughput is a closely related concept, but it's subtly different. It's an actual measure of what we get from the link. Now, as with any infrastructure, a network link can either be saturated or underutilized. In the former case, performance is impacted, but in the latter case, it may be that we can reduce costs or give up some of our bandwidth to somebody else who needs it. Probably the most important metric for an application, however, is latency. The definition of latency is deceptively simple. Simply how long does it take my traffic to reach its destination? But there are many factors that impact that. Bandwidth or throughput is a key, but that also depends on the number and capacity of individual links between the server and the client. Equally, the efficiency of the network devices on that path and the choice of the path itself are key. Also at play are the other consumers of that network capacity. Jitter is a measure of how reliable that latency metric is. In a LAN environment, jitter will be low, but in a WAN environment, some jitter is to be expected, and it can have unexpected effects. Finally, we have to consider packet loss. It's a real, if transparent, issue. Fortunately, networks are more reliable than ever, and protocols take care of most of the trouble. But in a performance-sensitive environment, packet loss could be the difference between making and breaking your SLAs. So to illustrate these metrics, let's look at a different kind of network, a traffic network, transport network. I'm based in the Midwest of Ireland, in Limerick City, and I've been working from home since before COVID made it popular. But my IBM base is in Dublin, which is about 200 kilometers away. And when I want to properly get away from things, I head for the Ivoire Peninsula. It's a similar distance, but the roads are very different, and hence the travel time. So while it's difficult to make out in the picture there, for the Star Wars fans amongst you, the Ivoire Peninsula was the location used for Luke Skywalker's hideout of Achto in the most recent trilogy. It's a gorgeous place to go and get away from things. Well, let's start with the easy journey. Both my home and the IBM campus are within easy reach of motorways and dual carriageways, which are the same as motorways but with a lower speed limit. If we first consider bandwidth, we can think of the speed limit of the motorway as being a measure of that bandwidth, although the number of lanes is an additional factor for motorway. In this case, the road probably has an engineering speed limit, which is akin to its theoretical bandwidth, and a lower speed limit that allows a safety margin, and we can consider that like our protocol bandwidth. So the motorway is analogous to a high bandwidth, low latency link. There is little to no congestion most of the time, and it's possible to fully utilize the maximum throughput of the link. Thanks to cruise control, the speed is consistent with little or no variability, so we have no jitter. The toll plaza in the middle of the journey is a good example of a processing restriction. The reduction in speed is very temporary, and it doesn't greatly impact the trip time, but it is noticeable all the same. Towards the end of the journey, more and more roads converge as we get to busier parts of the networks. Here, speed limits, or rate limits in terms of networking, and congestion impact the total journey time. So overall for our journey, we have a trip time of about 2 hours for an average of 100 kilometers an hour, assuming I don't stop for a coffee. The journey to Kerry, while a more inviting destination, is a lot less smooth and takes a whole lot longer. In this case, on paper, the journey is shorter, and while the maximum speed is slower, most of the journey is still theoretically possible at an average of 100 kilometers an hour. So the initial stage of the journey is on motorway again, so we get the gain of high bandwidth and low latency. Very quickly, we hit a traffic bottleneck, however, and all the gains of the motorway are lost. While the bottleneck is passed, we soon come to a stop. Unfortunately, one of the kids feels a bit carsick, kind of like a packet error. And as the journey progresses, it's not possible to make full use of the speed limit. So due to either traffic on the road or the quality of the road, it's not possible to make full use of that speed limit or the bandwidth. Throughput drops and there's a huge variability in speed, so we get jitter. Ultimately, however, we arrive with no packets lost on the way. In the end, however, for a shorter distance, we end up with a travel time that's nearly twice the work journey due to a combination of congestion, throughput, and jitter. In a database context, we could easily have a similar issue, where our link to the outside world is fast, but the destination for our data is not easily reached. All that said, however, while it's important to look at latency and bandwidth metrics, it's also important to say you shouldn't get fixated on them and try and be flexible with them. Networks themselves are more flexible than roads, and sometimes the job at hand means a mixture of different characteristics can be considered. If you're shifting bulk data, then high bandwidth is more important than latency. If you're doing real-time transaction processing, then latency is our primary concern. So low latency and high bandwidth is always good. Low latency and low bandwidth is probably always bad. But what about mixing the two? Well, really, this brings us to the topic at hand. There's a spectrum of possibilities in there. So if we can simulate the network effects on DB2, then we can answer the question of how much is enough? Or put another way, what kind of network do I need? So we'll move on to the performance and operational impacts on DB2. So where does DB2 see the impact of poor networking? Well, first and foremost, clients notice the network impacts when they're processing queries, specifically at fetch time. So if we consider the three phases of a query, we have our prepare time, our execute time, and our fetch time. Fetch time is most noticeably affected by network delays because that's when we're actually bringing back the bulk of the data. Another area where DB2 gets impacted is around authentication. So while we initially think of authentication at login time, DB2 continuously revalidates users throughout their session, and the delay in authentication can have subtle but noticeable delays throughout the query throughout the user's session time. From a resilience perspective, the sync mode we can use with HADR is dictated by both latency and bandwidth. First of all, do I have enough bandwidth to move the amount of data I need that are present in my transactions? But more importantly, do I have the latency to not have a significant impact on my original transactions? Similarly, if we're accessing a federated source or if we're using external tables to read and write data to cloud object storage, the amount of data we have to move and the time it takes to move them are factors in deciding whether those links are viable to use or not. As a final example, Db2 pure scale stretch clusters. The feasibility of these is very strictly a function of latency. The further we move the clusters apart, the longer and longer it takes for each of the individual network operations to execute. While this time individually may not be long, cumulatively, it can mean that we can no longer meet our transaction targets, transaction response times targets in such a design. So here are some examples of situations I've dealt with both in the lab and with customers where the network impact was a significant consideration. A few years ago, when I was testing some Db2 warehouse on cloud instances with identical workloads, I noticed that a newer, more powerful instance wasn't performing as well as an older instance. So while the absolute differences weren't huge, the relative differences were. In this case, the better system was taking about a third longer to complete the tests than the slower system. So when we delved deeper into the performance metrics, we identified that the fetch times were the biggest component of this performance loss. The execute times were, as expected, better. And ultimately what we just realized, it wasn't a great discovery, what we realized was that our services were provisioned in different continents. And while geographically there wasn't a massive difference between where our client was and the two services, the networks were different. And what we ended up with was an issue with latency. So the lesson here is to be wary of where you place your services. The second example relates to a customer who was exploring Db2 warehouse on cloud and moving their data warehouse into a cloud environment. During a POC, they reported significantly degraded performance times on some of their BI reports, which was something of a surprise to us because the sample queries they gave us all performed better in the cloud. Again, delving into the individual phases of the query, we discovered that extracting the data from the server was taking a long time. And what we discovered from that was that some of the reports, going back to a non-premise server, were pulling large volumes of data, in one case over 500 megabytes of results. And when we accounted for the network effects, we were able to demonstrate that performance was actually better than expected. And when they moved the reporting server in parallel to the cloud, performance of the overall solution was better. Continuing the examples, during another POC, worked with a retail customer who had significant ETL processes running throughout the day. Not so much a batch window as a no batch window. There was very little time during the day when they weren't actually working batches. They were actively migrating to cloud services and it provisioned what they felt was a high bandwidth network link of several hundred megabits per second. But as the workload metrics were gathered, it was unclear if they would have enough capacity to meet their SLAs. So they needed a way to simulate what they were doing into the cloud. As a final example, again referring back to a pure scale stretch cluster, I worked recently with a European customer who wanted to deploy a stretch cluster for OLTP operations. On the face of it, the distance wasn't huge. The data centers were separated by about 15 kilometers of distance. Cable distance was a little bit longer. But the key thing was that this was a high write activity workload, meaning lots of network interaction. The question here was, were the data centers close enough to support the query response times that their applications needed? So all of these examples illustrate just how key the network is to successful business operation. So let's move on to the meat of things, how we simulate network effects. So what we're going to talk about here primarily and where we derive this ability to simulate is from Linux traffic control capability. So the Linux kernel handles network scheduling and traffic shaping. And traffic control is the name of the user space application we can use to interface with this. It allows us to configure different types of queues, whether they're for priorities or for different scheduling mechanisms. And it allows us to shape traffic by introducing rate limits or delays. It also allows us to classify different kinds of traffic if we require. And what TC gives us is a hierarchical model of rules. So we can specify classes of traffic, We can specify rules based on sources and destinations, and we can specify effects that we want to apply to traffic. And in many respects, we do this in a similar way to what you might see with IP tables and firewall rules. So let's delve a little bit more into the structure of traffic control. So there are three core components to traffic control. First and foremost, we have a queuing discipline, or what's called a queue disk. And this controls how traffic is processed. It shapes it, which allows us to apply rate limits and delays. It can schedule traffic. Some queue disks are simple queues, such as a FIFO queue or a round-robin queue. Some queue disks can apply effects, such as applying a delay to traffic or applying a rate limit. Some queue disks can do both, and we'll look at some of these in later slides. Classes allow for a sophisticated combination of queues and queuing disciplines and network effects to be created. So it allows us to mix the best of things like rate limits or scheduler types. Filters then match packets to classes and consequently a set of effects. Most commonly we do this on IP header fields, but there's huge capability within the TC structure because it's closely mapped to the kernel to do this. But for the most part, we'll stick with IP traffic fields. Importantly as well, queue disks can be, or traffic control is applied to both ingress and egress traffic. So there's slightly more work to manage it to ingress traffic, but what we do is we control traffic on exit from a network device. So the diagram on the right gives you an example of a class hierarchy. In this case, where we start with the network device, ETH0, and we create some classes underneath it. So we create a rate limited class heading for port 80, or the web port, of 6 megabits per second. And we apply a filter that applies that web traffic into that class. But we can have a subclass underneath that, which maps SSH traffic to class 110, which is further restricted to 2 megabits a second. So in this way, we can create kind of quality of service hierarchies if we want. So as I mentioned, there are many different types of queue disks, some simply representing queues, so for example, fair queuing or control delay. But for the purposes of what we're doing with DB2, we're going to talk about three different classes. The first is token bucket filter. And this is an example of a queue disk, a queuing discipline that is very simple to use and allows you to control both rate and delay. It's simple because it's what we call classless. That means you can't create a hierarchy underneath it. What TBF does is it ensures that no more than a specified amount of traffic can leave through a network interface in a given time slot. The next queue disk we're going to look at, and more useful for QoS setups and flexibility, is called hierarchical token bucket. Now HTB allows us to control rates as well as creating classes. The last queue disk we're going to look at and use here is called NetEM, or network emulator. And in a way, it's very straightforward. It allows you to emulate wide area networks and the effects you see in them. So NetEM is an example of a queue disk that deals only with effects rather than scheduling. So it allows you to define delays, to define jitter, effects like packet reordering or packet loss. These can also include an element of random behavior, which is something that the other queue disks don't allow. So you can randomly sample a 10% variation in jitter from a normal distribution or a more sophisticated distribution, which allows you to simulate even more realistic scenarios. So which queue disks to use depends on the desired effect. For example, TBF controls traffic rates, as I mentioned, by limiting the amount of traffic through a port at a given time. But if you don't hit that limit, no delay applies. NetEM, by contrast, delays all traffic, regardless of whether it's the first packet or the 10,000 packet. So that's a lot to take in. And before delving into the examples, let's take a quick look at the anatomy of a TC command, because that's what we're going to use in some of the later scenarios. So TC is the core command, and we use this in all circumstances. But regardless of what kind of structure you're going to create, there are some common elements. Firstly, there's always the subject of a TC command. Secondly, we define an action that we want to take. The third element of the command is the object that will be impacted, and this is always a network interface. The next element is the position in the class hierarchy. Even in a simple configuration, we'll always specify that we're operating at the root of the traffic control structure, as in this example, or we specify where in the tree we want to build. Finally, we specify the effect that we want, and generally this is another QDisk and the parameters we want to apply to that QDisk. In this example, we want to apply a NetEM QDisk. We want to delay all packets by 265 milliseconds. If we delve a little bit deeper into the command, in terms of the subjects, so we can see that there are three types of subject mapping to our three control structures. There's always a QDisk, there's a class, or there's a filter. The actions are, as you might expect, we can add a rule, we can change a rule, we can replace a rule. Or in the case of QDisks, we can link a number of QDisks together. For the position element, we specify whether this rule is the first rule for this network device, or if it's part of a hierarchy. So if it's the first, we specify that it's the root. We might specify that it has a parent and let the system give it a default name, or we might specify it's the parent and give our own name, which is the handle. If we're dealing with classes, we specify a class ID instead of a handle ID. And finally, for the QDisk subject and the parameters, we can specify lots of different things. So in this example, as I mentioned, we have a NetEM with delay. We could specify a type of queue, whether it's a FIFO queue or a round robin or a priority queue. If we're creating a filter, we might specify rules here around matching traffic, such as the source or destination IP address or the traffic type. So the question comes up then, if we can simulate, where should we simulate? Well, any Linux installation can use TC because it's a part of the core installation and kernel. It's packaged in the IP root 2 table, which is default on every system. So we could deploy this on the client or the app server. We could deploy it on the Db2 server. If, for example, you don't happen to have a Db2 server, or sorry, a Linux server, you could use a proxy server, such as HAProxy or Nginx. And this would allow you to apply only egress configurations and works for a variety of scenarios where you don't want to touch either the application or the database server. Or the other option, which we'll use here, is to do it all on the Db2 server, using both ingress and egress rules. So the environment for this session, and it's worth mentioning that all the things I'm going to show you have been tested on Red Hat Enterprise Linux version 8 using Linux kernel 4.18. I used VMs, but you don't have to use VMs. You could use containers, you could use bare metal machines. And in all cases, I had simulated 10 gigabit network links. In order to use NetEM, I had to install the module kernel modules extra, or the package kernel modules extra. That is not default in Red Hat 8, whereas the NetEM requirements are default in Red Hat 7, and possibly in other distributions as well. And finally, it's worth mentioning I did all these tests using an early access release of Db2 11.5.5. So hopefully soon we'll see 11.5.5 on GA, but many of you may have looked at the early access release already. So let's look at some of the scenarios. So the first scenario we're going to look at is about restricting latency and dealing with a remote Db2 server. So this is an increasingly common scenario where we move a Db2 instance to a cloud environment, but the scenario is equally applicable to moving a Db2 server to a new DC, or any occasion where the client and the Db2 server are geographically separated. To keep things simple, we'll focus in this first example on latency only. We'll look at bandwidth in a later scenario. One way to do this is to use an ingress filter on the traffic arriving to the Db2 server. This has the advantage of not requiring input from any other team or expertise in any other application servers or operating systems. So you can do what you want, when you want, and for only the systems you want. And this puts the control to you, the Db2 professional. The first step in this scenario is to enable us to control inbound packets to the service. The structure of traffic control is that we can shape, filter, and classify traffic that's leaving a queue, which is egress traffic, or leaving a network device. In general, ingress traffic, which is coming into the device, can only be policed or rate controlled. Of course, Linux being Linux, this doesn't have to be an obstacle, and it provides a construct called the intermediate functional block that we can use to redirect the traffic that's flowing into a device through this pseudo network device IFB can be enabled and disabled dynamically. We show that in the slide there using the command modprobe IFB. Then what we do is we bring up the network device, IFB0. By default, 2 IFB devices are enabled when the kernel module is loaded, but you can configure it to just create one. And in these examples, we'll only be using IFB0. The next step before we can make use of the IFB device is to configure a queue disk that can process the ingress traffic through the network adapter. In this case, what we do is we create a queue disk on our inbound network device, which is ENS33. And we create this queue disk to manage its ingress traffic. So once the IFB device is in place and we're ready to do something with the ingress traffic, we configure the system to pass that ingress traffic to the IFB. And to do this, we use a filter construct. So the filter is applied to the network device and it matches all the traffic that we are interested in taking action on. You could choose to apply no particular filters on this, in which case all inbound traffic is restricted. That's probably not the best idea because even your SSH sessions will get slow and you may only want to restrict traffic coming in from the particular device. So we see the command here. If we look at it again, we say we create a TC filter object and we're adding a rule. So we're adding a filter on device ENS33. In this case, we're going to say that the filter is at the root. So we use a construct called parent FFFF, which creates the filter at the very top of the hierarchy. We then apply some rules, which is that we're going to use IP protocol to create a filter match. The U32 construct enables us to match on any IP header. In this case, we're matching all conditions. So we're matching all inbound traffic. And the action we're going to take is we're going to mirror all that traffic or redirect all that egress traffic back to IFB0. So the command looks complex, but fundamentally what we're doing is we're taking the inbound traffic and we're redirecting it through IFB. So the final step in simulating the latency is to add the delay. In this case, we're going to use the network emulator queue disk. For a simple case like this, we could use TBF to simulate latency, but for me, NetEM is a bit more intuitive. Additionally, while we're only using a simple latency delay here, we might want to use some of the more advanced capabilities, such as introducing jitter or random variations that we might see in the real world. So in this case, while we've redirected all the traffic to IFB0, what we do is we add a queue disk on IFB0 at the root of IFB0, so it applies to all traffic, and we introduce a delay of 265 milliseconds. And we can do a simple test to make sure this works. So in this example, we can see from another client, we can see that when we ping the server, we have a delay. Instead of a 1 millisecond ping time, we have a 266 millisecond ping time. So that's the OS level impact. So ping shows that the network delay is working, but let's look at the impact on Db2. So in this example, I've used the sample database shipped with every instance created from Db2 SAMP. So there's not much data in the database, but you don't need much to see the delay in action. In this case, the emp photo table has only 3 columns and 8 records, but each row has about 100 kilobytes of data. So what we do is we capture some query times using Db2 batch, or you can do it using your tool of choice. And what we have on the slide here is using no delays on the left with the latency of approximately 1 millisecond, and some results on the right-hand column with the latency of about 266 milliseconds. So what we see is that we fetch our 8 rows, but by introducing that long delay, we go from a 60 millisecond elapsed time for the query to 2.7 seconds. So that impact may not look like much, but consider that this is a small result set, and for some applications, the increase in elapsed time would render them inoperable. Now, you might say also that 265 milliseconds latency is unrealistic. A decent network provider should be able to deal with that. But consider that the approximate round-trip latency for a fiber connection is 10 microseconds per kilometer. If I select, for example, that my app server is in Athens and my database is in Dublin, that's a distance of approximately 3,000 kilometers. And suddenly I have at least 30 milliseconds extra latency per packet before accounting for any indirect routing or device latencies. This has noticeable impacts on even compact traffic like the select statement being transferred or the results of the execute phase before we even start to fetch results. And in case anyone's wondering, the 50 millisecond latency version of this will still have an elapsed time of 0.54 seconds, or nearly 10 times what the unrestricted result is. So to finish up the scenario, let's review the commands that we used in this section. While it took a couple of slides to explain it, you can see that it's, relatively speaking, only a few short commands to implement. So the first step was to enable the IFB device using modprobe IFB. The second step was to bring up an IFB network device so that we could apply TC rules to it. In the third step, we created a queuing discipline added to the default device, ENS33, that allowed us to control ingress traffic. The fourth step then was to apply a filter to traffic arriving on ES33 to redirect it to IFB0. The final step was to add a delay on all traffic exiting through IFB0. In this case, the delay is specified at 255 milliseconds. You might notice that the filter command is slightly different to the filter command I showed earlier. Whereas the first command restricted all traffic, the subsequent command restricts traffic only originating from my Db2 client and only target heading towards my Db2 service port. Be careful when you're applying delays. In an unrestricted environment, my SSH sessions were practically unusable because each key press resulted in a long delay before any response. Fortunately, I had a VMware console beside me so I could bypass the delay. But when you do apply inbound delay rules, just be careful that you target them specifically or you could end up with a difficult to control system. So let's move on to a second scenario where we look at restricting bandwidth only. So remote storage is an increasingly popular option amongst our customers, and DB2 11.5 introduced external tables, which could allow us to access delimited files via SQL. So these can be located on the server or they can be located in cloud object storage. For cloud object storage, there's a number of options. We can deploy them in Swift compatible sources, such as IBM Cloud Object Storage, S3 compatible data stores, such as AWS S3 Service, or again, IBM Cloud Object Storage, or even in Azure Blob Storage. And frequently, customers are using these increasingly for things like archive, for data exchange, or to facilitate ETL processes. The practicality of using external tables with cloud object storage is really governed by bandwidth. And the core question is, can I get access to the data I need in a timely fashion? That can be pushing data up to the cloud object store for onward ETL processing, or it might be that you're retrieving data from an ETL for use in your ETL processes or in your batch processes. Key to this question is determining the minimum amount of bandwidth you need. So one way of doing this is to restrict the bandwidth and incrementally increase the bandwidth cap until you find what your minimum requirement is to satisfy your business requirements. So to do this, we can use token bucket filter or hierarchical token bucket queue disks, as we outlined earlier. So the first thing is to identify if the external table you're using will be a read table, a write table, or a read-write target. We can use ingress filters to control read speed, or we can use egress filters to control write speed. So we might use a combination of filters here. So in this example, we're going to use hierarchical token bucket to restrict the bandwidth. HTB allows us to specify both hard and soft rates in which to limit the bandwidth. If you specify a soft rate, you're putting a cap on the bandwidth that's used, but you're allowing it to share bandwidth beyond that if nothing else is using it. If you specify a hard ceiling, it is literally the cap at which you can do. If you specify your soft and your hard bandwidth limits to be the same, then you're putting an absolute limit on the amount of bandwidth that traffic can use. HTB also allows us, as I mentioned earlier, to create a classful structure, which allows quite refined or fine-grained setups. And this facilitates a quality of service setup. And that may be of interest to some people where if you want to ensure that outbound traffic, say to a cloud object storage, is not swamping the network link or is not impacting other traffic too greatly, you can use a QoS setup to make sure that you restrict that traffic to an acceptable level. So at a high level, the approach is to configure a HTTP queue disk on your network device. Then we create a class hierarchy with bandwidth rules. And as before, we use filters to assign the traffic to a network class so that it can be controlled. So let's go through the steps. So in this example, you notice that the network device names are slightly different. The host is slightly different. And that was just due to an issue that I had with accessing cloud storage, so I used a different virtual machine. So the first step is we create a queue disk on our network device ENS160, and this queue disk is going to be called, this queue disk is applying at the very beginning. I'll see if we can underline it here. So this queue disk is being applied to the root of the network interface, and we're going to give it a name or a handle by which we can refer to it, which is 1. And we are creating a HTTP queue disk with no other options. And we don't need to specify other options here because what we intend to do is to actually specify limits elsewhere. In the second step, what we do is we create another queue disk, we create a class here. This class is going to be placed in the hierarchy below the parent we just created, below the HTTP queue disk we just created, and we're going to give it a reference ID of 11. In this case, we do specify some options. We're going to specify a hard limit that says we can use the maximum bandwidth of this network. So what we're going to do then is, as a kind of a quality of service idea, we create another class, this time for handling general traffic. We do create no restrictions on this class 111. So now what we want to do is we want to create one last class. This is class 121. And it is also going to sit in the hierarchy in parallel with general class. But this time we are going to restrict the bandwidth. We're putting a very tight cap of 56K, kind of throwing back to the US robotics modem days. And finally, we specify a filter to assign the class, assign the traffic to the specific class. In this case, I'm restricting traffic heading for the IBM Cloud Object Storage Service, and I'm going to send it to my rate limited class here. So in this example, I moved a small table containing some historical data to an external table that was backed by IBM Cloud Object Storage. The unrestricted link gives over a data network. Start this one again. In this example, I moved a small table containing some historical data to an external table that was backed by IBM Cloud Object Storage. The unrestricted link is over a data network with a nominal 200 megabits a second upload speed. And as you can see, it took sub-second time to transfer the data. While the 56K limitation is extreme, it does serve to show what you can do with bandwidth restrictions and how you could use different rate limits to determine what bandwidth you need. In this case, moving the same amount of data over the restricted link took 1 minute and 4 seconds. If you have business SLAs that say you must read or write data within a particular amount of time, you can use these bandwidth limitations to figure out just exactly how much bandwidth you need from your network providers and from your network team, what must be guaranteed as a minimum, or what must be a floor below which you can't go. So in our last scenario, we'll look at combining some restrictions, in this case Db2 HADR. As I mentioned at the beginning of this presentation, the feasibility of HADR depends on a number of factors, such as the latency and the bandwidth. We can also mention jitter in here because it impacts the latency. So when you need to simulate something like HADR, you need to combine these factors, these constraints. So there are really two questions when you're looking at HADR and networks. First of all, is what synchronization mode can my network support? But the corollary to that is what network does my synchronization mode need? So I might have a business need that says I must use sync or near sync, but the question is, can my network support that? So in this example, we build on the two previous examples, but the major difference is that your transactions are now very much reliant on the efficiency of the network communications. So we simulate this using a combination of HTB, hierarchical token bucket, and NetEN QDisks. And we're going to use ingress and egress restrictions. So the commands on this slide show the egress rules to be applied to traffic to the secondary. So getting my pen again here. So in this case, we're going to add a QDisk at the root of our outbound network to allow traffic to create a hierarchical structure. We then apply the same kind of rate limits as we did before, creating a default class. And then we add a device, another class, that introduces a more realistic rate limit. In this case, we want at least 100 megabits. We'd also like to take advantage of a surge capability to 150 megabits. So this might simulate an example where you have a quality of service arrangement with the network team that gives you a guaranteed minimum, but the ability to float above that if available. The next thing we do is we create a filter that redirects traffic to our secondary, going to our HAD or port, and redirects it back up through this limited class here. The extra component in this QDisk for these egress rules is to introduce a delay. In this case, we introduce a relatively simple delay, and we add an amount of jitter, 5 milliseconds, and we allow for some variation in that, some random variation in that. For the ingress rules, well, you have a choice here when you're doing this. If you want to, you could apply, so these would be the egress rules from the primary to the standby. You could apply a similar set of rules on the standby server that apply to egress traffic coming back to the primary. Alternatively, you could use ingress rules as we had in our first example, where we introduce an IFB device into the hierarchy, and you could restrict inbound traffic from your standby server back into the primary. So in this way, you can work on one server or two servers, and it really just depends on where you want to apply the control. So that represents the three core scenarios that I wanted to cover. But there are other scenarios that we can apply this in. So I've mentioned Db2 Pure Scale Stretch Cluster, or GDPC, Geographically Dispersed Pure Scale Cluster, a number of times. So GDPC is a cross-site active-active Db2 instance intended for transactional workloads. What makes GDPC different to the other scenarios we've covered is that it has both elements of Db2 communication, but also elements of spectrum scale communication, because we use spectrum scale to replicate the file systems from one side to the other. As I mentioned, there's a practical limit on separation. We have 10 microseconds per kilometer of fiber latency on round trip time. And a Db2 Pure Scale cluster must manage some interactions at the Db2 level between the coupling facilities and between the members. So internal communicate, it's not just traffic coming from the client, it's internal communications between the Db2 services. Similarly, spectrum scale as a software solution is managing the replication of storage. So our ability to replicate, to the speed at which we can replicate disk writes is also a factor in this, as well as Db2 structures. And that brings us to a question of how far is too far. We can use TC to control, to simulate this if you don't have network devices in between. So we can apply traffic control points at various sites. We can control the Db2 traffic going through from the traditional switch. And we can also apply TC restrictions to the spectrum scale service and restrict its ability to talk to the other side. And that gives us the ability to simulate or emulate the wide area network between the sites for both Db2 and for spectrum scale. This example is a little bit more complex, and I appreciate that you've already seen a lot of complex commands. So I hope to write an article on this and publish it soon, and that might serve as a guide to how you can apply both some of the simpler commands that we reviewed and also in a more detailed scenario like this one. Finally, for some other scenarios, I mentioned authentication as being a potential bottleneck in DB2. And this is something that some clients have experienced in negative situations, not due to network performance, but potentially network performance could be an issue, particularly as some companies are starting to move their authentication services to cloud-based environments. So you can use TC egress rules to simulate slow lookups from a DB2 server to an LDAP server. Similarly, QREP might be another scenario that you could examine. You can use traffic control capabilities to simulate the impact of latency, and again, to validate the bandwidth requirements. So to summarize, network performance, as we've discussed, is critical to the overall performance of DB2. It's one of those things that we find difficult to simulate and difficult to control. It's not like some of the other systems where we can test it ad infinitum or test the maximum performance capabilities. Simulating our network performance enables us to do a number of things. It enables us to validate an architecture that would be suitable to meet our business needs. It allows us to determine the resources we require to achieve the business goals, whether that's bandwidth, latency, or any other aspect of network performance. It also gives us a platform by which we can test the resilience of our system to network interruptions and plan for those scenarios in business critical environments. And to finalize, Linux traffic control gives all the tools that we need. And it gives us to do these simulations, and it puts them within the control of the DB2 professional. So that's been a lot to take in, and I hope you found it useful and somewhat accessible. There's a wealth of material online about traffic control, but if you have any further questions on the presentation or the content, please feel free to ask in the IDUG forums, or please reach out to me at my email address there. Thank you for your time and enjoy the rest of the conference.